It's 2026. Heat waves test cities that never planned for them. Power grids juggle new electrification loads. Farmers from India to the Sahel track rains that no longer follow a calendar. In rooms you never see, governments and operators are betting that AI, used carefully, can turn chaos into control. Today we're going deep on how AI is used against three connected challenges: climate change, energy reliability, and food security. We'll look at what's real, what's hype, and what it takes to make these tools work on the ground. Over the next 35 minutes, I'll show how AI helps run power grids, predict disasters, guide farmers, and shape insurance and finance. And I'll be candid about risks and limits that rarely make it into press releases. Think of a triangle. Climate drives extremes: heat, drought, floods. Those extremes stress energy systems and hit agriculture. Then the way we produce energy and grow food feeds back into climate through emissions and land use. It's one system. AI does not fix climate change. What it can do is improve prediction, optimization, and decision-making in systems that are too complex for manual control. In the US, EU, Japan, Korea, the push is integrating renewables and stabilizing grids while decarbonizing industry. In India, Southeast Asia, parts of Africa, and Latin America, it's leapfrogging to cleaner systems while expanding access and protecting vulnerable agriculture. The grid has one job: match supply and demand in real time. Solar and wind are variable. The more renewables a grid wants, the more intelligence it needs. AI models forecast electricity demand using weather, day of week events, even transit data. Parallel models forecast renewable output block by block, cloud cover for solar, wind speed for offshore turbines. Operators then schedule flexible resources: batteries, hydro, gas peakers, or demand response to keep frequency steady.
Offshore wind in the North Sea. Turbine clusters push real-time feeds into machine learning models to predict the next hour's output. U.S. utilities model EV charging surges after work hours and shape load with tariffs and smart charging APIs.
The more renewables you want, the more intelligence you need. AI is becoming that intelligence layer. AI flags anomalies in sensor data long before a failure. Temperature spikes, harmonics, odd vibration signatures. Crews fix small issues before they become blackouts. In many emerging markets, similar tools also detect non-technical losses, power theft, or failing meters, restoring revenue and improving reliability. Energy is the backbone, but intelligence on the grid is only part of the picture. Let's talk climate and disasters. Traditional climate models are accurate and compute heavy. AI steps in as emulators that approximate complex physics faster, and as downscalers that turn coarse global outputs into city-level forecasts. Faster scenarios let planners test heatwave responses, stormwater upgrades, or industrial siting in weeks instead of months. For cities and utilities, lead time is the new superpower.
Picture a coastal Southeast Asian city. An integrated platform ingests satellite feeds, ocean temperatures, and upper air winds. The system nudges the cyclone cone days earlier and tighter. These systems update flood risk in near real time, simulate wildfire spread, and recommend where to pre-position supplies for which roads will likely close.
They're game changers where forecasting capacity is thin, but they still rely on data availability and connectivity. Precision agriculture uses imagery, soil sensors, and weather to treat fields as many microfields. Large US, Brazilian, European, and Australian farms are early adopters. Platforms deliver per-field recommendations that raise efficiency while cutting inputs. A maize farmer in Kenya or a rice farmer in India uses a simple app. Behind the scenes, AI reads satellite and weather data, then suggests when to plant, how to irrigate, or what pests to expect. Benefits: better yields, lower costs. Constraints: phone access, data costs, trust, and localization. Beyond the farm, models forecast regional crop output from remote sensing and climate signals. Governments and NGOs use these to anticipate shortages, stabilize prices, and plan imports or aid before a crisis. Losses from storms and fires are rising. AI blends claims history with high-res hazard maps to price risk more accurately. Real-world implications. High-risk zones may face higher premiums or reduced coverage. Verified resilience, elevated structures, defensible space, flood-proofing can lower premiums when data proves the benefit. Companies use AI to ingest energy bills, sensor data, logistics, and supplier disclosures to estimate emissions with fewer blind spots. Then optimization tools suggest retrofits, renewable swaps, or route changes ranked by cost per ton avoided. In carbon markets, AI helps verify whether projects, like forests, actually deliver the promised reductions. Governments and investors are increasingly tying finance to these data-rich metrics. Many of the regions most exposed to climate impacts have the weakest data infrastructure. Models trained on richer regions can misread local reality. Overconfidence in a neat dashboard can be dangerous. Most cutting-edge climate AI capacity sits in a handful of countries and firms. That concentration can create dependency. Transparent partnerships and knowledge transfer matter. Also, AI itself uses energy. If training and inference run on fossil power, we're shifting problems, not solving them. The responsible path is clean power, data centers, plus efficient models. We covered how AI runs grids, predicts extremes, guides farming, prices risk, and measures emissions. The theme is amplification. AI amplifies resilience if we design for inclusion, reliability, and transparency. It amplifies risk if we don't. Action steps by audience policymakers: invest in data, infrastructure, open standards, and public interest models. Pair early warning with last-mile delivery, alerts that reach real people. Businesses pilot one concrete use case: grid efficiency, precision AG partnership, or emissions tracking. Start with a guardrails-first design. Operators and builders document KPI, lift, and risk controls. Share playbooks, communicators and citizens. Learn how these systems work so you can scrutinize them, explain them, and demand better ones as a clean brand interstitial. If you found this useful, subscribe to Sync Podcast and share this with a colleague who needs a practical map for the next 12 months. For templates, governance checklists, and strategy sessions, visit syncconsultants.com. Links are in the description. Picture this. It's a boiling summer evening. The air conditioners are on full blast. Electric cars are charging. AI data centers are humming away in the background. And somewhere, a grid operator is staring at a wall of screens, hoping the lights don't go out. At the same time, a farmer thousands of miles away is looking at a dry field, wondering if this season's rain will come on time, or at all. And in a glass tower in a financial district, a risk manager is staring at a map of coastal properties, asking how many of these will still be safe to insure in 10 or 20 years. These stories all sound very different, but they are now connected by one thing: AI. In this video, you're going to walk through 3 real-world case studies. How AI is quietly running parts of our power grid, how AI is helping farmers try to stay ahead of climate shocks, and how AI is changing the way banks and insurers think about climate risk and money. By the end, you'll see exactly how these systems work and where the opportunities are if you're an entrepreneur, a policy person, or just someone trying to understand what's really happening behind the AI hype. Let's start with the grid. Let's start with the grid. Imagine you're in a control room in a large US utility. It's 2026 and the screens in front of you show live data from thousands of sensors: power demand, line temperatures, wind speeds, solar output, and now the electricity draw from massive AI data centers that run 24/7. On one screen, a graph shows tomorrow's expected demand hour by hour. It's not just a guess from an engineer. It's a forecast from a machine learning model. This model has been trained on years of historical data, customer usage, weather, holidays, big sports events, even patterns from previous heat waves and cold snaps. It also knows roughly when new data centers are scheduled to come online in different parts of the grid. Every 15 minutes, the model updates, predicting how much electricity each region will need in the next few hours and over the next day. The utility uses those predictions to decide which power plants to fire up, how much backup capacity to keep, and when to buy or sell power on the market. Now look at another set of screens. These are focused on wind turbines and solar farms. Here, AI models are digesting weather forecast data, satellite images, and real-time sensor readings from turbines and panels. How strong is the wind likely to be at each site tomorrow afternoon? How much cloud cover will reduce solar output in the next few hours? Are any turbines vibrating in a way that suggests a future failure? The AI creates very detailed forecasts of renewable output, sometimes down to 5 or 15-minute intervals. With older methods, these predictions were much less accurate. That meant the grid had to keep more fossil fuel plants running just in case. With better AI forecasting, grid operators can lean harder on renewables without risking blackouts. They can run fewer backup plants, which saves fuel costs and reduces emissions. Forecasting is only half the story. Once the system knows roughly what demand and supply will look like, it has to solve a giant puzzle. Which plants should run? How should power flow across a network of thousands of kilometers of lines? This is where optimization comes in. Modern grid optimization tools use AI and advanced algorithms to figure out the best mix of generators and the best routing of power through transmission lines while respecting physical constraints, line limits, voltage levels, maintenance schedules. Think of it like a huge Tetris game where each piece is a power plant or a transmission line, and the AI is constantly rearranging the pieces to keep the grid stable at the lowest cost. Sometimes this reveals hidden capacity, lines that could safely carry more power under certain conditions, or backup units that aren't actually needed because forecasts are strong. That means utilities can delay expensive grid upgrades and still meet rising demand. Now, add one more twist. AI data centers are not just big power users. They can also be flexible. Some forward-looking utilities and cloud providers are experimenting with systems where data centers shift non-urgent AI training jobs to times of day when there's more wind or solar on the system, temporarily reduce load, or move workloads to another region when the grid is under stress. AI helps coordinate all of this, predicting grid conditions and scheduling compute tasks accordingly. Suddenly, a data center can act like a battery or a flexible factory, a problem in one scenario, a stabilizing asset in another. Opportunities in the grid story. For your viewers, here's where the opportunity is. Utilities and grid operators need tools for renewable forecasting, grid optimization, and flexible load management. Data center operators can earn money and goodwill by offering grid services, not just consuming power. Startups can build software that plugs into both sides, turning AI-heavy infrastructure from a threat to grid stability into a part of the solution. Now, let's leave the control room and head to the farm. Picture a small farm in Rwanda's Kayonza district. It's a few hectares of land, mostly maize and beans. The farmer doesn't have a weather station or a team of agronomists, just a basic smartphone and years of local experience. Rain has become unpredictable. Some seasons bring drought, others bring floods. A couple of bad harvests can push a family into debt or force them to sell livestock. A group of researchers, development agencies, and local partners decide to try something ambitious. Build an AI-enabled support system for these farmers. First, they start collecting data. Satellites pass overhead, capturing images of fields every few days. From these, they calculate vegetation indices, numbers that indicate how green and healthy the crops are. Rainfall and drought indicators are pulled from global climate datasets and local weather records. In some representative plots, they install soil moisture sensors connected through simple IoT devices. All this feeds into machine learning models, random forest models, in this case, that learn to predict yields and drought risk based on patterns in the data. When they test the system, the predictions track real-world yields surprisingly well, with high R2 and low error. What they've created is a kind of digital twin of the farming landscape, a data-driven map that can estimate what's happening in fields even when no human is there to see it. Predictions alone don't help if they stay on a server. So the team turns them into advice. Farmers get SMS messages or app notifications like delayed rains expected, consider planting drought-tolerant varieties, or adjusting your planting date. Soil moisture low. If irrigation is available, water in the next 3 days. High risk of a specific pest. Here are recommended actions. Extension workers, local experts who already support farmers, use dashboards that show which villages are at risk of drought or poor yields. They can focus limited resources where they're needed most. Crucially, the system doesn't replace local knowledge. Farmers still decide what to plant, but now they have more information. Here's where it gets even more powerful. In many countries, traditional crop insurance is too expensive for smallholders. Adjusters can't visit every field after a drought, and insurers don't have good data to price risk. Using the AI system's yield and drought estimates, a cooperative introduces revenue index insurance. Instead of paying claims field by field, payouts are triggered when the model shows that yields in a region have fallen below a threshold or when rainfall indicators cross certain levels. Farmers pay a modest premium, often bundled with seeds or fertilizer. If the season goes badly, the system automatically calculates payouts, reducing disputes and administrative costs. Because risk is clearer and more objective, local savings and credit cooperatives are more comfortable lending to farmers. They can see in data how risky a given area is and design loans accordingly. What changes on the ground? Over time, farmers in the pilot see fewer surprise crop failures because they get earlier warnings, better decisions on planning and input use, a financial safety net through insurance, and more tailored credit. The system is not magic. It depends on connectivity, trust in the model, and continuous data updates. But it shows how AI can turn scattered satellite images and climate data into something a farmer can actually use. Opportunities in the agriculture story. For your viewers, here's where the opportunities lie. Building localized agritech platforms that mix AI with simple mobile UX for smallholder farmers. Partnering with cooperatives, NGOs, and microfinance institutions to bundle advisory, inputs, and parametric insurance. Working on data infrastructure from sensors to satellite integration that makes these AI systems robust beyond pilot projects. Now let's walk from the fields into the world of finance. Imagine you manage a global real estate portfolio for an insurance company or a pension fund. On paper, everything looks fine, but then you overlay climate projections. Higher flood risk here, more intense storms there, wildfires creeping into new regions. You realize that a significant chunk of your portfolio could be exposed to climate impacts over the next 10-30 years. You need a way to quantify that risk and make decisions. Which assets are still good bets? Which need retrofits? Which should you gradually exit? This is where platforms like AlphaGeo come in. They combine three things: hyperlocal climate analytics. The system ingests hazard data, flood maps, wildfire probabilities, sea level rise scenarios, heat stress indices at very fine spatial resolutions. It uses AI and geospatial analytics to assign each property a risk score for different perils under different time horizons. Financial impact modeling. Instead of stopping at high or low risk, the platform plugs these scores into financial models. It adjusts operating costs, insurance, energy, maintenance, expected downtime, and even tenant churn due to climate-related disruptions. Scenario and adaptation simulation. Users can test what-if scenarios. What if a coastal city invests in seawalls? What if a building is raised or retrofitted? The platform recalculates asset values given these protective measures in different climate pathways. Zurich Insurance Group used AlphaGeo's tools to evaluate climate risk in real estate investments. Here's how that process looks. Step 1. Mapping exposure. They fed portfolio data, addresses, building characteristics into the platform. AlphaGeo overlaid hazard maps identifying properties most exposed to flood and extreme weather. Step 2, exploring adaptation options. For high-risk assets, Zurich modeled possible adaptation measures, improved drainage, flood barriers, or even relocating critical equipment to higher floors. Step 3, integrating into returns. The platform translated each adaptation option into changes in expected losses, insurance costs, and asset values. This made it possible to compare retrofit and keep versus sell and reinvest elsewhere in a hard numbers way. The result? Climate risk stopped being a vague red flag and became a set of quantifiable scenarios the investment team could act on. Zoom out, and the same kind of analytics is being encouraged by central banks, regulators, and green finance initiatives. Supervisors want banks and insurers to perform climate stress tests on their portfolios, essentially run simulations of what happens under various climate scenarios. AI makes it possible to do this at scale and in more detail, rather than relying on a few rough averages. Insurers are also using similar tools to refine underwriting, pricing flood or wildfire insurance not just by zip code, but by specific property characteristics and microlocation. Banks are starting to adjust interest rates and loan covenants based on climate risk signals from AI-enhanced models. Opportunities in the finance story. Here's where opportunities show up: building data and AI platforms that integrate geospatial climate risk, regulatory reporting, and financial modeling in one workflow, helping smaller banks, insurers, and asset managers who don't have in-house data science teams adopt these tools in a usable way, identifying and financing resilience projects, from flood defenses to building retrofits, where AI analytics show strong long-term returns. So, stepping back, what did you just see? In the grid, AI is the brain helping match electrons from renewables and data center loads second by second, deciding where power should flow and when. On the farm, AI transforms satellite images, weather data, and soil readings into actionable advice, insurance, and credit for some of the world's most vulnerable farmers. In finance, AI turns climate risk from something fuzzy into numbers that move billions of dollars, changing which buildings are insured, which projects get built, and which assets are future-proof. The common pattern is this: AI doesn't replace experts. It gives them a radically clearer picture of complex systems so they can act earlier and more intelligently. If you want more deep dives like this into real AI deployments beyond chatbots and hype, hit subscribe, share this with someone who's still asking whether AI is just a trend, and drop a comment on which of the 3 stories you want a full visual breakdown on next.